amplitude modulation, conventional amplitude modulation. Okay, and I told you that this distance is 2V minimum. Okay, this distance is 2V minimum. Okay, this distance is 2V max, and we are going to write modulation index m, which is Vm by Vc or Am by Vc in terms of V max and V minimum. Right? This is not something different. It's the same thing. We are representing modulation index, okay, in terms of this distance and this distance. See, if you look at this waveform, okay, what suddenly comes into your mind is this distance and this distance, right? Right? Yes or no? If you look at me, you see my belly first, right? Yes or no? Right? Like that, in this waveform, this distance and this distance is the one which can be easily noted. That's why you're going to take the readings from the CRO when you do it in the lab. Just take this distance and this distance, then calculate the modulation index. That's the only purpose. To calculate modulation index from the waveform, we use this. That's all. Okay. So we have expression. Okay. Modulation index is equal to V max minus V minimum divided by V max minus plus V minimum. Okay. So here I have taken it as A. In some books, all these might have been taken as V. Both are safe. Okay. Just a presentation. That's all. Hope you are understanding this. Fine? Okay? Yeah. Now, based on the value of m, okay, we get different types of modulation. Right? Based on the value of m, we get different modulation. Okay. Now, can you see that when m is equal to 0, okay, can you tell me what happens when m is equal to 0? You get only carrier, yes or no? Right. See, if you come to this equation also, now see this equation. Suppose m is equal to 0, what is S am of t? Yes, am of t is equal to AC cos omega ct. Yes, no. What is AC cos omega ct? AC cos omega ct is just a carrier signal. That's all. Right? Okay. Now, when m is equal to 0.5, okay, it is actually called as perfect modulation. Right? Your modulation index has to be between 0 to 1, not 0, 0 to 1, not including 0 and 1. Right? Okay. Now you can see when m is equal to 1, okay, it almost looks like a double sideband suppressed carrier. Yes or no? Right? And see what happens when m is greater than 1. See here. When m is greater than 1, okay, we call it as a over modulation. And can you get back your original signal from this? You can't, because of this, it is going to take this peak also when you recover the signal. Right? How do you recover AM wave? AM wave can be recovered by taking the peaks. Suppose if I take this peak, all the peaks, I'm going to get back this waveform. This is going to be your message signal. Right? Right? See this, if I take all these peaks, this peak, it is going to give you this signal. And this signal is your message signal. Right? Now, okay. Now, when m is equal to 1, also, okay, we can get the signal. Can you see here? But m is equal to greater than 1. Can you get back the signal, original signal? See, it is from here to here, it is okay. But here it is giving you some extra thing. Can you see here? That is not your original signal. Your original signal is a sine wave like this, but it is going to give you something like this. See, something like this. That means over modulation has to be avoided. Right? That means your modulation index has to lie between 0 to 1. Right? not including 0 and 1, but 0 to 1, right? 0.1, 0.2, 0.3 also fine, 0.4, 0.5, 0.6, 0.7, 0.6. I've understood this, okay? And you have one more example here. Can you see this is a MATLAB generated example? Okay, it's a MATLAB. And this modulation index is also measured in the form of percentage, right? 50% means 0.5, 100% means 1, 80% means 0.8. Okay, so we call it as percentage modulation. It's called modulation index. Have understood this? Okay. This is also going to show you effect of modulation index, right? What happens when the modulation index is above 1, when it is 1, and when it is less than 1. This is what waveform you get. Fine. Okay. I think in experiment number 1, have you varied that m in that simulink? Vary that m. Okay. There is a constant there, right? M, modulation index. It is modulation index. Double click on that. You can change the variable and then see what waveforms you get. I will try to demonstrate it here now. Okay, fine. So before that, let us go to some other. Okay, this is the AM transmitter. Okay, one of the crude pre-vacuum tube AM transmitter. You know, have you heard about vacuum tube? Where you heard about vacuum tube? Old. Even when I did my engineering in second year, I studied vacuum tube transistor. Right? It's all removed now, not there at all. Okay. See, this transistor which you are seeing nowadays in the lab, okay, or diode which you are seeing in the lab, during olden days, it was made out of vacuum tube. Right? You must have seen the old radio. Inside that, you must have seen that vacuum tube, which is working on the principle of cathode rays and all. Right. So that older that the first vacuum tube, pre-vacuum tube AM transmitters, you can see there now how they used to transmit an AM wave. Okay. Typically, they have used this. Okay. So it is in 1906. This is also first vacuum tube based AM transmitter built in 1930. Okay. Anyway, after that, all of you know that how this transistor, once the transistor has been evolved, now you get the radio. You have something called software defined radio nowadays, right? Now radio is coming to your mobile phone, right? Right. It's called software defined radio. Software defined radio is something different than what is this? What you're learning here, right? I've understood this. That is totally a different software defined radio. Okay. You are able to get the radio in your app, right? Yes or no? Does it have any receiver? No. It is receiving only data, and that data is played. It's called software defined radio. Software defined radio. Okay. Okay. Now let us see some parameters. Okay. Of course, whenever we have a system, we talk about the efficiency. Yes or no? What is the power consumption? Yes or no? It's an electronic system. Yes or no? See, you are actually modulating a carrier according to the message signal. Yes or no? Right. You have seen the waveform that your carrier amplitude is varied according to the message signal. Who does it? Who does it? Some electronic component. Yes or no? Electronic component does it. Okay. Now, of course, it's a system. You have to see its efficiency. We see how much power it is, power dissipated. Everything you have to see. Okay. So now let us see about those parameters. Okay. Modulation efficiency. Okay. Modulation efficiency is ratio of useful power transmitted divided by the total power transmitted. Now see which is useful and which is not useful here. Right. That's modulation efficiency. Now can you see in the equation of AM wave, you have also carrier component in that, but it will come based on the principle we have arrived to an equation. In that equation, carrier wave is there. It will definitely come, right? So we have something useful and not useful in the output, that's in the EM wave. So now efficiency is something like useful power, ratio of useful power transmitted divided by total power transmitted. Right. Now total power is equal to power in the carrier, power in the upper side band, power in the lower side band. Right. Out of these three, do you require carrier? Carrier is, it's not useful at all. Right. So now what we do, if we take the power in the side band divided by total power, okay, that is going to give you the modulation efficiency. I have understood this. Power in the side band divided by total power into 100 will give the modulation efficiency. Right. Now, what is PSB? P suffix SB? P suffix SB is the power in the side band. Power in the side band is equal to, it is the sum of the power in the lower side band plus power in the upper side. Okay? Power in the lower side band plus power in the upper side band. What is PT? PT is the total power. That is power in the carrier, power in the power in the upper side band plus power in the lower side band. Right? That's going to give efficiency. Now, how much is the efficiency? From where we can calculate this power? Right? See the equation. See the equation. See, you have the equation of AM wave given by SAM of t is equal to AC cos omega CT plus MEAC by 2 cos omega C plus omega MT plus cos omega C minus omega MT. This is what the expression you got. Now out of this, can you find out the power? You have equation. You have, suppose V of t is equal to, okay, V cos omega t. How do you find out the power in that? You all know it, right? Root mean square, right? So what is the power? Individual power. Can you see how see this is what the equation. You have carrier component is AC cos omega CT. Carrier component is AC cos omega CT. This is upper side band. This is lower side. Okay. Now, what is the power in this? It is AC square by 2. Yes or no? Right? Power in this AC square by 2 root mean square value. Right. So power in the carrier is AC square by 2. Right? Okay. So PC is equal to AC by root 2 whole square. Right? Because this is max value, no? We have to convert it into RMS value. That's why we are using root 2 here. Have you understood this? Okay. So AC square by root 2. See, we are actually trying to dissipate this SAM of T into a resistance of R value is equal to 1. Right? What is the power is equal to what? It is VC square by R, right? 2R, actually say 2R, right? Okay, right? So now that R considers to be 1 ohm. Considering R to be 1 ohm, the power in the carrier, this component, power in this component is equal to, why it is AC by root 2? Why it is AC by root 2?
So the root mean square value will be
so
taken.
AC by root 2 whole square divided by R is there, but that R is equal to 1 ohm. That's why we are not writing there. So hence, the power in the carrier is equal to AC square by 2. Power in the carrier is equal to AC square by 2. Okay. Now can you tell me what is the power in this? So MAC by 2 divided by root 2 whole square divided by R. That will be AC square M square divided by 2 root 2. So that is going to give you AC square M square divided by 8. Hope you are understanding, no? Right? Now see, now power in upper side band is equal to power in lower side band, yes or no? Power in upper side band is equal to power in the lower side band. Now, power in upper side band is also AC square M square by 8. Power in lower side band also AC square M square by 8. Now, what is total power? Total power is equal to this power plus this power plus this power. Right? What is sideband power? Sideband power is power in the upper sideband plus power in the lower sideband. Now, can you get me the equation value of efficiency? What is modulation efficiency PT? Modulation efficiency PT is equal to power in the sideband divided by total power. Now, can you tell me what is the value? Can you do it yourself? It's very simple. You have everything here. Right? Hope all of you understood how I got power in the carrier, power in the upper sideband, and power in the lower sideband. Just your simple. This is what you studied in your electrical science, right? How do you find out the power? Yes or no? Right? Okay. This is what you get. Yes or no? Now, modulation efficiency. What is the equation for modulation efficiency? Modulation efficiency is equal to, see here, sideband power is equal to power in the upper sideband plus power in the lower sideband. Okay, divided by total power. What is total power? Total power is equal to carrier power plus sideband power. Now, just solve this equation. This is sideband power. That is AC square m square by 4. Okay, and this is carrier power plus sideband power into 100%. So if you solve this, you get m square divided by m square plus 2 into 100. So this is the equation for modulation efficiency. Fine. Okay. Now you can take an example. Suppose m is equal to 0.5. If suppose this modulation index is equal to 0.5, that means 50% modulation. Okay. What is the value of efficiency? Efficiency is equal to 11.1%. Yes or no? Right? Now, when modulation index is equal to 1, efficiency is equal to 33.3%. See how this modulation index is related to efficiency. Right? Can you check whether you are getting 11.1%? It is 0.5 square divided by 0.5 square plus 2. Just check the values. You are getting 11%, right? Yes or no? If you are getting 11%, 11.1%. When m is equal to 1, it is 33.3%. Okay. Now there is a small question over there. Can you write that question? This question. Write this question. Suppose 100 kilowatt power is transmitted in EM waves, right? Then only 33.3 kilowatts of the transmitted power resides in the sideband, and remaining 66.7 kilowatts power is wasted in the carrier. Okay. What this is going to tell you now? Okay. How much is wasted actually? Tell me, as a carrier, right? See. 66.7, see, 100 out of 100 kilowatts. See, your power transmitted to an antenna is 100 kilowatts. Out of that, how much is required actually for transmitting your signal? Only sidebands. That is where you have your message signal and the carrier signal. Right. Now, your AC cos omega c is unmodulated carrier. Yes or no? In this equation, what is AC cos omega ct? AC cos omega ct is unmodulated carrier wave, right? Of course, cos omega c plus omega mt and cos omega c minus omega t, that is what actual modulation. There you have both your message and the carrier. But this AC cos omega ct is the only carrier. But what to do when you try to generate AM, that also will go along with that. I understood this. That's why that double sideband suppressed carrier AM wave is used, where carrier is not there at all. Yes or no? That's what I told you in my last class. Right. Double sideband suppressed carrier wave. In double sideband suppressed carrier wave, carrier will not be there at all. Last class, hope you remember how do you generate double sideband suppressed carrier wave? I told you this.
Multiply the carrier
How
and
do you
message.
generate double sideband suppressed carrier wave?
So multiply the carrier and
Just
message.
multiply carrier wave with the message signal. Right? You will get double sideband suppressed carrier wave. It's called DSB-SC. That is the way you suppress the carrier. Now, once again, you have two sidebands. Imagine you have suppressed the carrier. You have used double sideband suppressed carrier. You have used DSB suppressed carrier. See, you have AM wave, conventional AM wave. Conventional AM wave has carrier in it. But in double sideband suppressed carrier AM wave, no carrier in that. You have two sidebands. Okay. But once again, two sidebands. Do you require this two sidebands? Not required. Only one is enough. Okay. So we call it as single sideband wave, SSB AM wave. If you remove one sideband also. See, your spectrum looks like this. Your spectrum looks like this. Suppose if I take sine wave as a message signal. Okay, if I take sine wave as a message signal, your spectrum looks like this, right? This is your carrier signal. This is Fc plus Fm. This is your Fc minus Fm. Right? Same thing is there in negative side. Okay, same thing is there. Now, this is your carrier wave. Right? Okay. Now, in DSP-SC, okay, that will not be there. Carrier component will not be there. Right? You have seen from the equation also, no carrier component. Okay. So, this will not be there for DSP-SC. Okay. This will not be there. This is the spectrum of double sideband suppressed carrier. Now, once again, you have this upper sideband and lower sideband. Do you need both? Not required. So how do you remove the one now? How do you remove the one? So if you remove either upper sideband or lower sideband, okay, then there will be single sideband. You will be having only this is Fc plus Fn. Suppose your spectrum is like this, okay? If the spectrum is like this, now this will be single sideband MP. Right? Okay. I have understood this. Fine. Okay. What happened? Okay. Don't worry. Okay. I have understood this. Okay. So we have now three types of modulation. One is conventional EM wave. Conventional EM wave, where there is a carrier, there is the upper sideband, there is a lower sideband. And we have DSB-SC, double sideband suppressed carrier, where we don't have carrier, we remove the carrier. I told you how to do it, very easy. Okay, see, this is multiplier, we call it the modulator. Okay, now actually mathematically we are multiplying this. Okay, and this will be your message signal m of t is equal to am cos omega mt, right? And here comes the carrier. The carrier will be your AC cos omega ct. Just multiply this. Right. When you multiply this, you will get a double sideband suppressed carrier wave. This doesn't have, this equation will not have any carrier component in that. Okay. Now after that, it will have lower sideband, upper sideband. Once again, two sidebands. You have to remove one sideband. So once you remove that sideband, it will become single sideband AM wave. So that is to be highly efficient because only one sideband is there in your transmitted AM wave. Right? I understood this. Okay. Now, how do you generate single sideband wave? Anyone has done single sideband SSB experiment? Definitely, you must have done it. How did it tell you? How you did single sideband? It's very easy. See here. Filtering method, yes or no? Listen. Here comes your signals and systems. Okay. See, this is the frequency axis, yes or no? This is frequency axis. This is S, D, S, B, S, C of F. Okay? This is the frequency axis. This is the spectrum of, try to understand, it's very important. This spectrum is very important. Right? Okay? Not only for Mr. Raja, who is the minister sitting out of the jail because of the spectrum scan, for everybody spectrum is very important. Okay, I don't know whether you really know that spectrum scan in India. Okay, I'm just reminding you. Okay, so spectrum you have to understand very well. Okay, now what is this? This is spectrum of DSP-SC wave. Yes or no? Spectrum of DSP-SC wave. See, this is minus FC. Now, how do you remove one of the frequency component in this? Use filters, right? You use filter. So how do you filter this? Multiply with the transfer function, okay, with a band pass filter. Do you remember 4 types of filters exist in the literature in DSP? One is low pass filter, one is high pass filter, band pass filter, and band stop filter. Right. Now that also, in band pass and band stop, we have different filters. It's called notch filters. It's called notch filters. Now see here, only single frequency has to be filtered out. Right? Remaining thing has to be removed. We need to have a transfer function which is actually only at this point. So we use the transfer function. See here, this is also in frequency domain. Now this is the transfer function of the filter. I'm just writing as H of F. This your H of F, okay, is something like this, exactly here, like this. And this is amplitude is 1. Fine. This is the frequency. This is FC plus FM. I'm going to keep only upper side band, and I'm going to remove all other bands. Here also, same thing will come here. See, in frequency domain, whatever I draw from 0 to 0 positive side, same thing will come here. Okay, same thing will come like this. Right? Have you understood this? Okay. Now see, when you multiply these two, when you multiply spectrum of DSP-SC and this H of F, can you tell me what will happen? This is multiplied, all these are 0, right? This is multiplied by 0, everything will become 0, but this is multiplied by 1. So only this frequency will be coming at the output of the filter. Have you understood this? So how do you generate now single sideband suppressed carrier wave? One way of generating single sideband suppressed carrier wave is, first you generate DSP-SC, right? How do you generate DSP-SC? I told you simple procedure. This will give you DSP-SC. This is your message signal. This is your carrier signal. This is going to generate DSP-SC. After that, here you use a band pass filter, which is called as notch filter, which has a very sharp band of frequency to be passed. Right? And the frequency, the bandwidth of that filter has to be around FC plus FM, so as to keep upper side band and remove lower side band. Okay, that is this one. Okay, so now you know that convolution in time domain is equal to multiplication in the frequency domain. All of you know about it. See, I'm just bringing you signals and system wherever is required. Right, this is a filter, right, and this is output. Okay, now I'm showing the same in the frequency domain. So it is now becoming multiplication, yes or no? Right? So you multiply these two. So what is coming here is this one. I'm in the frequency domain. Try to understand this. I'm talking from frequency domain point of view, not time domain point of view. Okay. So this is the spectrum of the signal which is available here. Right? Now the transfer function h of f is this one. Right? Now what is the output? It is multiplication of the spectrum of this by this. Right? And what you get the output here is the filtered signal in the frequency domain. Now how do you get into time domain afterwards? Take the inverse Fourier transform, you'll get the time domain. So that is what your signal is. That's what your single sideband AM wave is. Now why single sideband AM wave? Why we need to go for single sideband AM wave? Because in conventional AM wave, we have unuseful things, yes or no? We have unuseful things. Like we have carrier. In conventional AM wave, you have carrier component, you have upper sideband, also you have lower sideband. Right. So now out of that only one is required. Right. So for that what we do? First we remove the carrier. What we get? When you remove the carrier, what you get? Double sideband suppressed carrier EM wave. Now double sideband suppressed carrier wave has got both upper sideband and sideband or lower sideband once again. Now one of the sideband you remove it. What we get? Single sideband EM wave. And how do you get single sideband EM wave? One of the method is filtering. There are other methods we'll discuss whenever we come to HTTP. Have understood this? Okay. So I think all three experiments you are doing it in the lab, right? Also, not only in the lab, and also you are doing it using MATLAB simulation. See, when you simulate it in MATLAB, see, don't simply copy and paste and get the output just for the sake of doing it. Just see how the program is written. I know that most of you just copy and paste some waveform you get. Just see how you are going to, because there is a compre exam for that. MATLAB also compre exam is there. Right. In compre exam, can you copy and paste? You can't do it. You have to write the program. Have you understood this? Okay. So you can escape till compre exam. But after that, you cannot by heart also. That's why I'm telling you, try to do it yourself and try to understand how you are done. Okay? Okay, so now, okay, so what is the equation? See now, total power is equal to, see here, total power is equal to carrier power plus sideband power. All of you know it, right? I'm just taking conventional EM wave now. When I write all the equations, I will take conventional EM wave. Okay, now, what is sideband equation? Sideband power is equal to AC square M square by 4, yes or no? Yes or no? Right, okay. Now you see here, I will just separate this, I will just separate this equation little bit. Okay. I will just write it in terms of AC square by 2 into M square by 2. Right? Yes or no? Okay, what is AC square by 2? What is AC square by 2? Carrier power, yes or no? Okay, so replace that as PC. Now, P sideband is equal to, you got an equation, M square by 2 into PC. Have you understood this? Okay, now substitute this PSB in the above equation. Okay, substitute this PSB M square by 2 into PC into this equation. This will become PC plus M square by 2 into PC. Fine. Take PC common. What you get? PT is equal to PC into 1 plus M square by 2. So what is the equation for total power now? Tell me. What is the equation for total power? Equation for total power is equal to carrier power multiplied by 1 plus M square by 2. Can you tell me what is total current now? I want you to tell me this answer. What is total current? Total power you have. Consider R is equal to 1 ohm. Exactly. So IT is equal to, okay, IC into under root 1 plus m square by 2. All of you understood this. You have power equation, right? The current, PT is equal to I square into R. Right? Okay. So you will also get an equation for total current. Total current. I have not written here. I expect you to write that in your notebook. So total current is equal to IT is equal to IC into 1 plus m, root of 1 plus m square, right? And what is this? What is this PT and IT? That is the current and power dissipated in your antenna when you just, how you are going to transmit your signal through an antenna. And all this is nothing but antenna current. That IT which you have is nothing but an antenna current, and PT is the power dissipated. More about antenna you will be studying in electromagnetic theory and electromagnetic fields and waves. I am not taking any antenna in this course. Absolutely no antenna I am going to discuss in this. We will be totally discussing it in the electromagnetic fields and waves. I have understood this. Okay. Okay. Now, for example, we have considered in earlier case for deducing all the equations, m of t is equal to only cos omega mt. Yes or no? Let us consider a message signal having multiple frequencies. Have you understood this now? Right? Earlier AM equation which we have done, that there we have considered only m of t is equal to AM cos omega mt. That's all. Now I will consider your m of t is equal to A1 cos omega 1 t plus A2 cos omega 2 t. This is nothing but your mixed frequency signal. So how many frequencies are present in this? There are 2 frequencies present in this, right? Right. Now can you write the power for this? Can you write the equation, AM wave equation for this? Tell me. Your AM equation will be AC cos omega CT. So can you tell me how do you get an equation for AM wave? This is your m of t. I just skipped the step there. I think you all know mathematics, can do better than me. You are studying 3 mathematics in 2 years. Yes or no? So your AM of t is equal to, see, AC plus m of t into cos omega ct, right? Now substitute this as the one which is given, right? And of course you use m is equal to AM by AC, right? So what you will get? Okay, what's happening? Anybody is controlling this from anybody's mobile? No, no? Okay. All of you keep your mobile inside. Right? How do you get this equation? From this, right? Okay. Now, can I see this equation? Can you write the power? What is this? You have upper side band and lower side band, right? You have upper side band and lower side band. Okay. Now, can you plot the spectrum for this? Can you plot the spectrum for this? Can you do the spectrum for this? You have 2 frequencies here. It's not 1 frequency, right? Upper side band you have 2 frequencies. Lower side band you have 2 frequencies, right? Okay. And then you have a carrier component. Okay. Now can you find out the power? Can you find out the power? Just think and do it. Don't simply copy. think and do it. It's the same thing which you have done earlier. Only the equation is changing here. I'm giving you one task to draw the spectrum of this. Okay, how do you draw the spectrum of this? How do you get spectrum? Tell me. Okay, so I think that time is getting over. I am giving this as a work to you all. Okay, I am giving this work to you all. Can you do it? Can you take a? Do you have a sheet? Okay, so all of you write a number in that. Okay, ID number. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 17. Okay. 17 names are to be there. Okay. First was to draw the spectrum. I think you don't have any problem in drawing the spectrum of this. Okay. Second one, from this equation you get the power, right? Now total power is equal to this one. Okay. Now we can just write it as Pc is equal to 1 plus mt square by 2. What is mt square? Mt square is equal to square root of this m1 square plus m2 square. Which one? This should be m2. Exactly. It's m2. Okay, there's some typographical mistake maybe there. Please, that's why I told you don't copy directly, right? Because these equations are all very difficult to type in PowerPoint. Okay, sometimes. Fine. Okay, so let's stop here. I think those